Good morning, everyone. My name is Sukrut Nadigotti, and today I want to tell the story of a paper that truly redefined what was possible in 3D perception for autonomous systems. So, we're going to be going into a deep dive into point pillars. We will look at the specific challenges in the field that the authors were wrestling with. We'll unpack their incredibly elegant solution piece by piece, and then we will explore the lasting impact it has had. My goal today is to show you how a brilliant change in perspective uh, showed a new way of representing data, which unlocked a new level of performance that the community is still building on today. So, to really appreciate point pillars, we have to travel back in time and basically understand the world that it was born into. The field of 3D object detection was stuck in a classic trade off. You could either be fast or you could be accurate, but getting both was the holy grail. It was nearly impossible. Yeah, the chart on the slide paints a very clear picture of this dilemma. You see the cluster for fixed encoders. These were methods like MV3D and Pixor that were fast, no doubt, but that speed it came from using handcrafted features. So engineers would essentially hard code rules in to interpret the point cloud, which limited the model's ability to learn complex patterns, capping its accuracy. On the left, you can see the learned 3D encoders, which was basically uh, star players like VoxelNet, which took the exact opposite approach. They learned everything from the data, which led to incredible accuracy, as we see, but it was also painfully slow because it relied on computationally heavy 3D convolutions. So you can see this gap, this goal or big empty box on our chart. This was to bridge the divide. Could someone actually deliver the accuracy of a fully learned model at the speed of a 2D pipeline? This was the $1 million question that our paper hopes to solve. So let's dig a little bit deeper into the bottleneck by focusing on VoxelNet. It's important to give VoxelNet its due credit because it's highlighted in the paper as one of the first methods to achieve true end-to-end learning in the space, and it set the standard for accuracy. You can see in the diagram here that a raw point cloud comes in, it's organized into a 3D grid of voxels, and then it's fed into a 3D CNN backbone. And that highlight in red is our bottleneck. The issue here is that LiDAR data is incredibly sparse, so most of that 3D grid is just empty space. So running dense 3D convolutions over this is very, very inefficient. And the result is that the paper stated that VoxelNet ran at just 4.4 hertz, which is a speed that was deemed too slow to deploy in real time. Its successor, Second, the name of it is called Second, made some fascinating improvements with using sparse convolutions, which got the speed up to a more usable 20 hertz, but the authors of PointPillars noted that even then, the fundamental problem of 3D convolutions remained. So this is where the story gets a little bit more interesting. Instead of trying to optimize the existing thought approach, the PointPillars authors decided to take a step back and change the rules of the game from the get-go. You can see here in the visual that it's kind of like a aha moment. On top we have that complex, computationally expensive 3D voxel grid, and the PointPillars insight was to simply collapse it. So instead of 3D boxes, they organized the point cloud into the 2D pillars that you see at the bottom. So a pillar is just a voxel with an infinite height. So this wasn't just a simplification, it was basically a strategic masterstroke. It completely removed the need to manually tune the binning of the vertical dimension, which was like a very tricky hyperparameter in other methods. But most importantly, it allowed them to take in all that rich 3D information within a pillar and learn to encode it into a feature channel representing a 2D pseudo image. So suddenly the problem was transformed. A very slow 3D challenge became a fast 2D one, which was perfectly suitable for the highly optimized 2D convolutional networks that the GPUs are built for. So, how did they build a network around this idea? The architecture is a very beautiful, simple, and modular, and it consists of three main stages. And this slide here gives the high level roadmap. First, the pillar feature network. This is their novel encoder and basically acts as the heart of the system. Its one job is to execute that brilliant insight we just discussed. So basically taking that raw point cloud and converting it into a sparse but structured pseudo image. Second, that pseudo image is fed into a standard 2D convolutional neural network backbone, a CNN backbone, and this network's job is to create a rich, high level feature representation just as it would for a regular camera image. Finally, a direction head, which is based on the popular SSD or single shot detector design, takes these features and does the final work of detecting and regressing the 3D bounding boxes. So for the next few slides, we're just going to unpack that first stage, the pillar feature network, because understanding it is key to understanding the entire system. Okay, let's start with the technical details. The process starts with pillarization. As you can see in the top-down grid in our visual, the XY plane is divided into a uniform grid. So the paper uses a resolution of 0.16 meters for this, but of course that leaves out the third dimension. So the next step is what the paper calls decorating the points. We see this in the visual. A raw 4D point with a X, Y, Z, and reflectance R is augmented into a fully 9-dimensional vector. So this vector not only includes the original data, but also the points distant to the arithmetic mean of all the points in the pillar. So that's represented by XC, YC, ZC. And the offset from the pillar's center is represented by XP, YP. So in an ablation study, the authors basically proved that using all 9 of these features was critical for the best performance. So finally, to create a predictable input for the GPU, the network needs to limit the number of pillars to 12,000 and then the number of points per pillar to 100. So this would create a dense fixed size tensor, which is essentially exactly what you need for efficient and parallel processing. So now we have this large, dense tensor. The next challenge is to learn a single meaningful feature for each of those 12,000 pillars. Our diagram here walks us through that transformation. So the network uses a simplified version of PointNet to do this. So it has a linear layer, which the paper points out can be formulated as a very fast 1-by-1 convolution, which is applied to every single point, followed by batch normalization and then a ReLU activation. So this would transform each 90 point into a higher dimensional 64 channel feature space. So now that we have those features for every point, not every pillar, this is where the aggregation step comes in. You can see in the visual, a max pooling operation is performed across the n dimensions. So the n dimension. So across all the points within each pillar, this operation would effectively ask for each of the 64 feature channels, what is the most prominent value among all the points in this pillar? So it's a very simple but powerful way to summarize the contents of the entire pillar. So the result, as you can see in the right, is a much more compact tensor with the shape. You can see 64p12,000. So we've successfully encoded all of the information from up to 100 points in each pillar into a single learned 64-dimensional feature vector. So now we're at the final step of the encoder, and this is where it all comes together. So the visual on the slide illustrates how the network takes those simple 12,000 learned feature vectors and scatters them back to their original pillar locations on a 2D canvas. So an index stored from the beginning tells each feature vector exactly which cell in the grid that it belongs to. So the final result there is a dense 2D feature map with the shape CHW. So this now looks just like the output of a standard convolutional layer in an image-based network, and it is ready to be fed directly into the 2D CNN backbone input. So the entire computationally brutal part of the problem, which was dealing with a sparse and unordered 3D point cloud, is now over. The rest of the pipeline can simply be used for fast, efficient, and standard 2D convolution. So now that we've seen the architecture, how is it trained? So this slide's visual splits the strategy into two key parts: the loss function and then data augmentation. On the left, we have the losses, where the total loss is a sum of three components adopted from the second paper. So LLOC is represented as a smooth L1 loss for regressing those 7 box parameters that we mentioned earlier. And LCLS uses focal loss, which has parameters with an alpha of 0.25 and a gamma of 2, which is critical for handling the massive class imbalance between objects and background. And LDIR, or L direction, is a classification loss to resolve the 180-degree orientation ambiguity. And on the right, we can see the data augmentation with that visual representation of those cars with the bounding boxes outlined, which basically states that this is critical for good performance. And we can see that most powerful technique here, often called GT-aug, or ground truth augmentation. So they created a database of all the ground truth objects from the training set, and then during training, they would literally paste these objects into new scenes. So this would dramatically increase the number of instances the network sees. And they also applied a whole suite of other augmentations like random flipping, scaling, and rotations, as well as pasting. So what were the results? So the architecture is clever and the training is robust, but what were the results? In short, they were dominant. In quotes from the paper, it was stated that PointPillars outperforms all published methods with respect to mean average precision. And we could see this in the table from the KITTI, or KITTI benchmark on the moderate difficult setting. So for a bird's eye view detection, PointPillars achieved a map, or mean average precision, of 66.19, which is a massive leap over second, which scored only 60.56. So for the much harder 3D detection task, it scored 59.20 MAP. Again, this clearly surpassed both VoxelNet and Second. So these numbers, they didn't just inch past the competition, they set a whole new state of the art for LiDAR-only detection, which even was beating most methods that used sensor fusion, and it did all of this while being incredibly fast. And this brings us to the speed, which was arguably the most revolutionary part of the paper. So Point Pillars achieved its state-of-the-art accuracy while running at 62 hertz. And we can see in this bar chart the whole story. So VoxelNet was at a slow 4.4 hertz, and second made a great leap to 20 hertz, but Point Pillars at 62 hertz just blew them out of the water. And we would need to take a look at the full runtime breakdown from the paper to see why. And we see that from the paper, the total inference time was 16.2 milliseconds. So organizing the points took 2.7 milliseconds, and uploading to the GPU took 2.9 milliseconds. But the novel encoder itself just 1.3 milliseconds. The 2D backbone took 7.7 milliseconds, and this proves it beyond a doubt. The encoder was no longer the bottleneck, meaning that the architecture is flexible, and by simply using a coarser grid, they could push the speed even further. So as you can see from the last bar, a faster configuration was able to match the old state-of-the-art accuracy while running at an incredible 105 hertz. So, to summarize, what makes PointPillars so great? First, I would point out its extreme efficiency. So by completely avoiding 3D convolutions, it delivered true real-time performance. Second, it had very, very high accuracy. It didn't just sacrifice performance for that speed. It set a new state-of-the-art using only LiDAR data. Third, its simplicity and generality. So by using pillars, it removed the need for hand tuning vertical binning. So the paper also notes that the learned encoder can be adapted to other sensors like radar without any code changes. So in an ablation study, the authors were able to prove that learned encoders like point pillars are strictly superior to fixed encoders across every single or all resolutions. Finally, it provided a strong modular baseline, and its clear three-part design made it the perfect foundation for future research to build upon. But no model is perfect, and a fair critique means understanding its limitations. So the paper's own qualitative analysis in section 5 was very transparent about this. The primary failure mode stemmed directly from its core design choice, which was collapsing the vertical dimension. By summarizing an entire vertical column of points into a single feature vector, this would mean that the network could sometimes lose that explicit 3D structure that would be needed to distinguish certain objects. So the most common failure is confusing pedestrians with other tall, thin objects like poles or tree trunks because their pillar representation could look very, very similar. It also would occasionally misclassify similar classes like pedestrians or cyclists, which can have a similar size and upright posture, especially from the abdomen upwards. And of course, it would also be subject to the standard failures of most detectors, like missing heavily occluded or very distant objects where the point cloud is extremely sparse. So it's a trade-off. The simplification that gives it its speed or its strength also would introduce these very specific ambiguities. So this brings us to the lasting impact of Point Pillars, which extends far beyond its own benchmark scores. Its true legacy is in its role as a catalyst for the next wave of innovation. Because it was so fast, accurate, and simple, it quickly became the de facto backbone for a new generation of 3D detectors. So researchers no longer had to worry about building a fast encoder. They could just use point pillars and then focus their efforts on designing more sophisticated detection heads. So this is what enabled the development of more complex and powerful architectures, like the highly successful and often recently talked about anchor-free model called Centerpoint, which maintains real-time speed. By providing a robust and open source foundation, Point Pillars was effectively able to democratize real time 3D perception and accelerate progress across the entire community of mobility. So, in conclusion, Point Pillars fundamentally solved the speed versus accuracy dilemma that had held back 3D object detection. You can see in summary that the breakthrough wasn't just a more complex model, but a smarter, simpler, and easier data representation. By collapsing the 3D point cloud into 2D pillars, it made high performance, real time 3D perception a practical reality. And the final sentence of the paper says it best. Point Pillars dominates all existing methods by offering higher detection performance at a faster speed. So it is a landmark work that shows that sometimes the most profound innovation comes from finding a simpler way to see the world. So thank you for listening to me and my presentation. This was Sukrut Nadigotti for mobility. And some of my sources, here's the Point Pillars paper source. I also use Adobe Photoshop and Canva to generate those beautiful diagrams that you were seeing. Thank you for your time.